In this problem, we have another 3D static equilibrium problem. And in this problem, I'm applying a force of 800 newtons at point A. Now, point A is also connected to three different ropes in 3D space. So it's connected to this rope AD, this rope AB, and this rope AC. So this problem seems a little bit more complicated than the last static equilibrium problem we did because these ropes are in 3D space. But if we follow the same procedure and we break up these ropes as forces along a line, and then we use our equations of equilibrium, we'll be able to solve it. Now, this will be a sort of a long problem, so the video will probably be a little long. First thing we want to do is we want to draw a free body diagram. And I want to draw a free body diagram about point A. When I draw a free body diagram about point A, I have a force F that's pointing upwards. And then I have each of these forces, AD, AB, and AC, and they're going to point back along the line since they're a force along the cable, since they're a force along the line. So this will be some force AC. This will be a force FB, and they point away from A since these are ropes and ropes can only support tension. So FAB, and then I have FAD. Now this is my free body diagram, and these are the four forces that I'm working with. After I draw this free body diagram, what I want to do is express all of my forces as vectors. Now this force F is the easiest. This force F is being applied upward, which is in the positive z direction. So my force F is going to be equal to 800 K. Now let's look at FAB. And FAB is a force along the line. FAC is a force along the line. FAD is a force along the line. What that means is for each of these forces, if I look at the equation for force along the line, my force, and this is the vector, is equal to the magnitude times some position vector over the magnitude of that position vector. We can get these position vectors right here by looking at the points of A and B, or A and C, or A and D, and subtracting them from each other, and that's going to tell me the position in space that this force is along. So let's do that. Let's get the positions of all of these points. A is going to be, well, I'm right at this origin right here, so I go 0, 0, and I go up 5. Where I go to B, I have B is going to be, I need to go 4 in the X, 4 in the Y, and 0 in the Z. All of these cables are in that floor plane. So I'm going to have 4, 4, 0. If I go to C, C is going to be, I need to go, well, I have to go in the minus X direction. So I have to go minus 2. Then I have to go positive 3 in the Y. So minus 2, positive 3, 0. And for D, I have to go, well, backwards 4, backwards in the y 5, so minus 4x, minus 5y, and again 0 in the z. Minus 4, minus 5, 0. Okay, so I've done half of this. I have all of these points, and now I need to figure out what the actual position vectors are. So let's start with AB. And for this position vector, AB, what I need to do is I need to subtract the head of the vector, B, from the tail of the vector, A. And that's going to give me 4 minus 0, I, this minus this, then plus 4 minus 0, J, this minus this, and then plus 0 minus 5, K. It's this minus this. So what I get is this is 4i plus 4j minus 5k. And I'm going to do the others just in one step. I'm just going to look at these numbers and get my position vector. So if I say my position vector of RAC, this is going to be equal to minus 2i plus 3j minus 5k. And for D, this RAD is going to be equal to minus 4i Then we have minus 5j. And then we have minus 5k. Okay, so now I found all of the position vectors, and now I need to find the individual magnitudes. So let's do that. So for my magnitude of this position vector AB is going to be the square root of all of this, the sum of the square of these terms. So I'm going to have 4 squared plus 4 squared plus a minus 5 squared. Let's do that. And I have to take the square root of that. So I have 4 squared plus 4 squared plus minus 5 squared. Take the square root of 57. And I'm going to round it to 2 decimal places. So this is going to be equal to 7.55. All right, let's do this position, the magnitude of RAC. That's going to be equal to the square root of minus 2 squared plus 3 squared plus a minus 5 squared. Minus 2 squared plus 3 squared plus minus 5 squared. Take the square root of 38. And I get, this is, let's go to 2 decimal points, 6.16. So this is 6.16. And then finally, this position vector RAD, this is going to be equal to the square root of minus 4 squared plus minus 5 squared plus minus 5 squared. And this just brings up a point. If I forget these minus signs, I'm still going to get the same when I square them. So minus 4 squared plus minus 5 squared plus minus 5 squared, I get 66. And if I had forgotten those minus signs, since these are sum of squares, so all of this, it still gets me 66. So when I take the square root of 66, I get this is equal to 8.12. Okay, so now I have enough information to figure out what my vectors are for each of these forces along a rope. Let's do FAB first, like this. So FAB is going to be, oops, and I forgot this vector over here, but FAB is going to be equal to, well, this force is unknown, so it's going to be FAB, and then it's going to be times, well, what do I have? I have this vector RAB, so for I plus 4j minus 5k divided by this 7.55. And this is going to be equal to, well, let's do that. Let's take the 4 and divide it by 7.55. And let's take a 5 and divide by 7.55. So this is going to be 0.533 FABI plus 0.533 FABJ minus 0.667 FABK. And now we need to do this for the other 2 vectors. So let's go to FAC next. So this is going to be FAC times, okay, now we need to use the right position vector, this minus 2I plus 3j minus 5k, and that gets divided by the 6.16. All right, let's figure out what those numbers are. 2 divided by 6.16 is 0.325. 3 divided by 6.16 is 0.487. 5 divided by 6.16 is equal to 0.811. So now we know that this is equal to, this is minus, so minus 0.325 FACI, and then we have plus 0.487 FACJ, and then we have minus 0.812 FAC with a K component. Finally, the last one, we have this force AD. So FAD is equal to this force FAD times, okay, now we need this position vector, minus 4I minus 5J minus 5K, and this is divided by 8.12. So let's 4 divided by 8.12 and 5 divided by 8.12. So finally, this is going to be equal to minus 0.493 FADI, and then we have minus 0.616 FADJ, and then minus 0.616 FADK. All right, so now we have all of our forces and they're expressed as Cartesian vectors. Now the only thing left to do is we have these three equations. Some of the forces in the x are equal to 0, some of the forces in the y are equal to 0, and some of the forces of the z are equal to 0 for particle equilibrium. And we can solve for our unknown forces. So let's first take the sum of the forces in the x and make it equal to 0. All right, now the x is going to be anything with an I component. So we have an I component here, here, and here. So this is going to be 0.533 FAB minus 0.325 FAC and minus 0.493 FAD. We are also going to have the sum of the forces in the y, and these are going to be equal to 0. So that's going to be anything with a j component, so j, 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 and 0.533 FAB plus 0.487 FAC, and then minus 0.616 FAD, and this is equal to 0. So I forgot right here, this has to be equal to 0. I'm going to need more room. So I'm just going to drag this down, and I have the sum of the forces. Actually, I'm going to need to go look at that. The sum of the forces in the z are equal to 0. So 800K, I have this force, this 800K force right here. That's going in the positive K. So I have 800, and then I have this. So they all have K terms, minus 0.667 FAB minus 0.812 FAC and minus 0.616 FAD. And this is equal to 0. So I have three equations and I have three unknowns. I'm going to need a little bit more room. So let me move this guy down a little bit. And what I need to do is I need to pick some of these variables to solve for. Nothing stands out to me as being amazing to solve for, so I'll just pick this and solve for FAB. When I do that, I'm going to have FAB is going to be equal to 0.325 FAC. I bring it to the other side of the equation, plus 0.493 FAD, and I divide by this 0.533. I'll need this equation, so I'm just going to star it, because when I have these two terms, I'll be able to solve for what FAB is. And I'll actually simplify this. So what I'll have is 0.325 divided by 0.533, and I'll have 0.493 divided by 0.533. So this is going to be equal to 0.610. I'll just round that. FAC plus 0.925 FAD. Now I have to take this equation right here, and I need to plug it in for the FAB right here. So what I'll get is I'll have 0.533 times 0.610 FAC plus 0.925 FAD plus 0.487 FAC minus 0.616 FAD is equal to 0. Now let's distribute this 0.533 and multiply it by 0.610 and 0.533 times 0.925. Okay, so now I have 0.493 FAC. I'm going to have 0.325 FAC plus 0.493 FAD plus 0.487 FAC minus 0.616 FAD, and that's going to be equal to 0. Now, if you look at this, I should only have two terms. I should have FAC, FAC, FAD, FAD. So I can combine these two terms together. So I'll have 0.325 plus 0.487. So I'll have 0.812 FAC, and then I'll have this 0.493 combining the FAD, so minus 0.616. I'll have minus 0.123 FAD. This is equal to 0. Now I need to solve for one of these. I'll just pick the first one, FAC. So I'll have FAC is equal to 0.123 FAD divided by 0.812. 0.123 divided by 0.812. And FAC is going to be equal to 0.151 FAD. Okay, now I can substitute that into this last equation. For this last equation, just need a little bit more room. What I'll have is this 800 minus, okay, now this also takes from here. So minus 0.667 times 0.610 FAC plus 0.925 FAD. And we'll do this one step at a time. so we hopefully won't make an algebra mistake, minus 0.812 FAC minus 0.616 FAD, and that's equal to 0. Now, I have an expression for this FAC, so I'll have 800 minus, let's distribute this out. So I'll have 0.667 times 0.610 and 0.667 times 0.925. So this will be minus 0.407 FAC minus 0.616 FAD minus 0.812 FAC minus 0.616 FAD. And we do have this expression now for FAC. And every time I see FAC, what I can do is I can plug this in. So I'll have 800 minus 0.407 times 0.151 FAD minus 0.616 FAD minus 0.812 times 0.151 FAD minus 0.616 FAD, and that's equal to 0. So I need to do a little bit more calculation. So minus 0.407 times 0.151. So this will be 800 is equal to 800 minus 61 point, oops, doesn't seem right. 0.407 times 0.151, 0.0614. FAD minus 0.616 FAD, and then 0.812 times 0.151. This is going to be minus 0.122 FAD minus 0.616 FAD is equal to 0. And now finally, everything's in terms of FAD. So I'm going to write it next to it. And we can combine everything. So we can combine it and we get minus 0.0614 minus 0.616 minus 0.122 minus 0.616. So that's minus let's make sure this is right. 0.0614 minus 0.122. Yep. So this is 1.41. When it comes to the other side of the equation, we're going to have 1.41 FAD is going to be equal to 800. So FAD is going to be 800 divided by 1.41. And that's going to be 567 newtons. And now we can back substitute. So when we back substitute, FAD is going to be equal to this number times 0.151. So this is going to be equal to 85.7 newtons. Oops. And we can back substitute again. And when we back substitute again, we can figure out what FAB is. So FAB is now going to be equal to, and I'll do it in a different color, is equal to 0.610 times 85.7 plus 0.925 times 567. And this is going to be equal to 576 newtons. 77 newtons. So there you have it. This tells us what the forces in each of these ropes are. So I'll write it right here. My force, AB, is equal to 577 newtons. My force, AC, is equal to 80, let's call it 85.7 newtons. And my force, AD, is 567 newtons. Hopefully this helped you with a 3D equilibrium problem. It's a computationally expensive problem, especially when you're doing this back substitution. There's lots of places of algebra mistake. I will show you in the next video, do a real quick video on how to use your calculator to solve these systems of equations very, very easily. So be sure to check out that video, and if you are allowed to, you can skip all of this back substitution with a calculator method.